Hi, welcome to another session on advanced algorithms. In the last session, we discussed an algorithm for computing the minimum cut of a graph, which was a conceptually very simple algorithm that just repeatedly contracts a randomly chosen edge, which means that these two vertices that form the edge are collapsed, and then all the edges that formerly pointed to x and y now point to the same node, which introduces in general multiple or parallel edges, and we just kept these in the graph. And then we found that if we repeat this algorithm until we only have two nodes with a single set of parallel edges in between, then this is always a cut in the graph, and with a certain probability, but actually not a very good probability, this is an optimal cut in the graph, a minimum one that cuts the smallest number of edges possible. Now we showed this theorem in detail last time, and then I already remarked that we need a quadratic number of repetitions before we get a usable algorithm, because the probability that we get for a single run is just too small, and I just wanted to add the proof for this fact, which is actually if we do and choose two independent repetitions, then what we find is the probability that all of them fail is that so 1 over n choose 2, that's the probability that a single run fails, which is a relatively large number, close to 1. But if we take that to the power of n half, then what we get is actually bounded by 1 over e, since this is a quantity that, 1 over. So this is a quantity like 1 minus 1 over n to the n, just with a substitution, and as this goes to infinity, it goes to e to the minus 1. And you can show that this is actually an inequality for every n. So we get a usable success probability, a constant probability to find the min cut with that many repetitions. If we actually would like to have an algorithm with a larger one, if we want to amplify that probability, we need even more repetitions. So in this basic version, the algorithm is actually an n to the 4 at least algorithm for the min cut problem, and as such worse than the best deterministic version. We can improve that. As we noted last time, the problem is that the probability to pick a good edge is strictly going down as long the more we have contracted the graph, because there's if we are still in good shape and have all the good cut edges in the graph, then there's still the same number, but the overall number of edges goes down rapidly. So the idea is, let's fix some function that we're going to choose in the end to optimize the running time. And we stop the contraction as soon as we only have a certain number of vertices left. And then we just, for the remaining small graph, we construct deterministically what the optimal min cut is. So for that, we use the cubic deterministic algorithm that I just noted last time that it exists. We won't discuss it here in detail. And then the overall running time can be shown to be essentially quadratic plus a term that's cubic in this cutoff parameter. And the probability for one of these runs is now not just 1 over n choose 2, but L of n choose 2 over n choose 2. So let's see how we can prove that. So let's first consider the success probability. We already had before that we keep the min cut the specific one that we have in mind, and in the worst case there's only one. That's exactly the probability of these events. That in the ith step we don't pick an edge from the actual min cut. Now in the modified algorithm, before we used to go down until n-2, until we have contracted the graph into a single pair of vertices. Now we stop it early by truncating if we have this size L of n. And by the same arguments that we've had before, the probability for each of these events is just given by the following. It's this 1 minus 2 over n minus I plus 1. So the idea was that the graph still has a certain cut of a certain size, then it has to have a certain number of edges, otherwise we could find a better cut. And by repeating that, we found this. Now we can just consider the product down to where we've been last time, and then divide again by all the factors that we actually don't have. N minus L of n plus 1 up to n minus 2, because these are the ones that we are actually skipping by the truncated algorithm. Well, and again by the same arguments as last time. The upper one is 1 over n choose 2. The lower one is 1 over L of n choose 2. And if you rewrite that, you get this bound from the theorem. Just ignore that Firefox wants to remind me that he started. Okay. That's for the success probability. For the running time, we note that this is just the probability to run this deterministic algorithm, and that's an upper bound for the running time of the complete contraction algorithm. As you show in the exercises, there's an implementation that achieves this O of n squared. So let me just add here that the running time is trivial. One contraction plus one deterministic run on, but now just a graph with L of n nodes. So that completes the proof. Now this theorem does not yet tell you how to use it. Of course, we would like to have a good algorithm with a reasonable running time. So how shall we put that into action? If we run n squared over L of n squared runs, so this is greater than 1 over the probability, that means that so many independent runs succeed with probability at least 1 minus 1 over e. That's by the same argument that we just had here. The probability that all of these runs fail is just less than 1 over e. And you just have a more complex function that you insert, but it's the same idea. If the success probability is some p, then 1 over p independent runs give you this probability at least. So what does that mean for the running time? So let's say we would like to have this constant probability of success guarantee for the moment. Then we have a running time for a single repetition times the number of repetitions that we do. And you can rewrite that as n to the 4 over ln squared plus, for the other term, n squared over L of n to the 4. No, sorry, I canceled the wrong way. It's actually n squared times L of n. Okay, so that makes 2 parts. And the asymptotic running time is optimal if the two have the same kind of growth. So what we want is that alpha is theta of beta for large n. And, well, if you think about that for a second, you find that the best you can do is n to the 2/3 as the order of growth for L. So, I mean, for the specific function L, you have to choose some integer valued function. So you would maybe do it one of these, but you can add a constant factor that doesn't change the O terms. And then if you insert that, what you get is O of 4/3 12, that's 8/3. Okay, checks out. And that's a good deal less than the cubic running time you had for the quadratic algorithm. However, we still only have this constant success probability, and we would need additional repetitions to make this a usable algorithm, as usual, as always. But the nice thing is, at least we beat the deterministic algorithm that we've not discussed here by a still pretty simple algorithm. The bad thing is we actually use the deterministic algorithm to do so. So unless we can implement that in a nice way, also our modified algorithm will not work. And there's another reason why we can do actually better than this. Let me add this sketch here. The point is that initial choices of edges are mostly good in the sense that they are not from the min cut that we would like to retain, whereas later choices have a much higher probability to fail. So what we should do is don't repeat these too often. And for the others, try those many times. As long as we still use the algorithm as a black box and repeat it many times, we are not able to do that. So graphically speaking, up to now, we've done independent runs all the time. But what would actually be better is to start, say, with 2 runs and then always branch. That automatically leads to the point that up here where the graph is large, you only do a few repetitions, whereas down there where the graph is small and you have a higher chance to fail, you do many more repetitions. And if you work that out, you find, so Karger here was joined by Cliffstein for this improved algorithm. You find this recursive algorithm. For small graphs, you just compute deterministically what the min cut is, but this is simple because it's just for very small graphs. That's much less a requirement than what we had before, where we had for an unknown function L of n that could be of any size, where we had to compute the min cut deterministically. And if the graph has a certain size, then we contract it down to a certain size. So the point is h is the target size of the graph. So what we do is essentially reduce the size of the graph by a factor 1 over square root 2. Okay, why this magic constant here comes up, you will see in a second. It comes naturally out of the analysis. So you contract the graph until it has only h nodes, and then you recursively call the same algorithm for this graph, and then you do the same thing again, but of course these random choices here must be independent. That's the idea. And then again you do recursively the same, and then you get 2 cuts and you just return the better one. And that intuitively just follows this pattern. You start such trees, and in each step you branch further. So whenever you go down in the size of the graph, you make sure that there's more repetitions. Actually, you double the number of repetitions whenever you reduce the graph size by this. And what you get by this is an algorithm that has essentially quadratic running time with just a log factor, and at least, well, better than constant success probability. So giving here a precise bound is a bit more challenging, but at least this tells you, if you repeat that a few times, it's easy to obtain an algorithm that has a high probability to give you the actual min cut. So let's prove this, and let's first look at the runtime, because that's simpler. The running time is given by a recurrence because we have a recursive algorithm. Well, if let's just write it's sum O of 1 if n is less or equal than 6. That was just the base case where we solved the problem by a deterministic algorithm, or table lookup if you like. The interesting case is that we have to do something. Then we do twice the same. Namely, we call the algorithm with a smaller graph, where we see that at least in an asymptotic sense. So a is essentially 1 over square root 2. The deviation here is that we add 1 so that this is never just 0. it wouldn't be 0 anyway, so it's never 1, so we make sure that this is always greater or equal to, which makes sense because we don't want our graph to be contracted down to a single node, then we don't have any cut left. But essentially what we do is we reduce the graph size by this factor, and what we pay for that is that we contract the graphs. Now again, we are just generous and add some term n squared. Let me just add big O off, so it's an upper bound only. So that was again the running time for a complete contraction of the graph down to two nodes. If we stop that a bit early, then the actual running time is a slight bit better, but probably not more than a constant factor. So this is, I guess the theta would still be fine, but we don't actually need that. Now, if you look at this from a master theorem point of view, on the first level you have n squared effort, then you branch into two cases where you have an as the graph size, so the tall function on the next level is an squared, so that makes 2 times a squared n squared compared to n squared. And since a is just 1 over square root 2, that's actually n squared again. So what this tells you is that on all levels of your recursion tree, in total, you do n squared effort. So you just have to take the height of the tree as a multiplicative factor, and that's why the master theorem gives you that this is O of n squared log n, because you have log n levels. If you reduce the size of the graph by a constant factor, if you like, so the height of this tree is actually just given by log square root of 2 of n, right? Because that's the reduction in size that you have. But for the O term, that doesn't make a difference. So that's the running time. How about the success probability? And that's actually a bit tougher to analyze. We write PL for the probability that these graphs that we produce, the two graphs that we produce in one step of the recursive algorithm, if they have the current size, so if n is currently L, so the probability that they still contain the min cut that we have in mind. And well, by this I mean one of the graphs. So you pick 1 or 2 here. It's just the probability is the same for both because it's an independent repetition of the same experiment. And so this is the probability that a single step in the algorithm, the contractions here or the contractions here, do not contract any edge in the cut. Then, as we've shown before, that's the same kind of reasoning, just inserting these wicked numbers. We have this choose 2 divided by L choose 2. Sorry, that's from the theorem about the truncated algorithm, started with size L and stopped with this size H. And well, you can cancel a bit the 2's, but it doesn't help too much. And you just find that this is at least 1/2, because this is just essentially, if you just look at the L's, then what you get is a factor of 2 here for the leading term. If you multiply out and just look at the coefficient of L squared, you get 1/2 here and 1 here, and the rest is just adding to this. So you find that in each of the steps, if you go down the tree, you have at least probability 1/2 to not destroy the minimum cut in one of the graphs. And if we write success n for the probability that the whole Karger-Stein Min Cut with size n, just small p instead of the graph, returns a minimal cut. So in particular, so I'm always referring to this one specific cut that we have in mind, actually. Then what we find is that our PL times the success probability for the smaller graph, for the recursive call, that's the probability that one of the two, well, since we used, well, PL is just this probability. So this is that one of the two runs returns C. Well, and actually it suffices if one of the two succeeds. So 1 minus this wicked term. That's the probability that one fails. That's the probability that both fail. And by that we essentially get a recurrence for this suck. If we call it with a very small graph, then there's nothing left to do. And well, for the other cases, this is the failure probability, so you have to take counter probabilities once more. And let me again here just drop the slide round off terms. Then, well, we actually already knew that this here is less than 1/2. So we can, let's use these cool features to copy paste that. Where we replace this by 1/2. Well, this is not such a nice recurrence as the one we've seen before, but you can kind of still solve it. You can show that every solution of this recurrence is 1 over log n. And so the success probability is at least 1 over log n, which, I was telling Bogus before I announced that this is actually better than a constant. Probability is of course worse. It's a lower bound, but this is going to 0. So without repetition, a single run of this Karger-Stein algorithm is actually not helpful. But this is only 1 over log n and not 1 over n squared as we had before in the original Karger algorithm. So that proves the theorem. And to make it a usable algorithm, we can use, well, log n repetitions, which then gives you constant probability. And if you want to do more, then you should maybe use log squared of n, or log n squared iterations. So of the whole thing as a black box now, right? Then, well, the probability goes to 1 as n goes to infinity. So that's something that will kind of work. And if you multiply this by the running time for a single run, you still get n squared log cubed. It's not so nice, but it's still a good deal better than the cubic algorithm without randomization. Well, at least for large graphs. So with this nice, clever application of sampling and repetitions by adapting the number of repetitions to actually the failure probability that we have in a certain single step, we close this chapter on randomized algorithms, and we proceed to the last big chapter of this lecture, which is on approximation algorithms, which are dealing with the case that you're solving a optimization problem, but instead of just enforcing an optimal solution, you can live with some solution that's at least close to optimal or good enough in a certain sense. But we would still like to have a provable guarantee of how bad the situation, how bad the solution can be in the worst case. Let's first, maybe before we discuss the examples, I should add, so this is for optimization problems. We discussed these a long time ago, and since you might have forgot a bit, let me just recap a bit what it was about without giving the formal definition again. So there's a set of valid instances for the problem, and for each instance we have a set, shouldn't be empty, of feasible solutions. So that's candidates for the optimal solutions, and we usually wrote m of x for that if x was the instance or the encoding of the instance. Then there was some objective function that we usually called cost. And this assigns to each of the feasible solution a value. And for our definition, I'd like to recall that we defined that costs are always integral. It might for some problems be more natural to deviate from that and allow rational numbers, but I think it's cleaner to stick to integral values in that case. And so we use the term cost or objective function here interchangeably. And then for this class NPO, that's the class of optimization problems where we at least have a chance to find polynomial algorithms. We can check in polytime the following things. If a certain, well, if X is a valid instance at all, or if we just give some gibberish encoding of a non-functioning instance, whatever that would be, we can decide whether a given instance is feasible, and we can compute cost of a given solution. If we can't even do these in polytime, there's no chance to optimize in polytime. Then also remember that we had the optimization version, which asks for an optimal solution from which we can easily compute also its value. Obvious, I think we called it evaluation problem. We also had the slightly restricted version that only asks for the optimal objective value. And well, initially we discussed that we can actually go back and forth between these two, and you've seen a few concrete examples where this was actually relatively easy. So if we can find the objective value, then we're actually already in good shape and happy with that. And usually finding the solution is then not as hard as coming up with the objective value itself. Okay, let me first go, before we discuss a concrete example, let's define what approximation actually should be. So you recall the formal definition of our optimization problems looked like this. I forgot to mention goal. We can minimize or maximize. That's something I guess you remember. An algorithm that was consistent for such a problem always had to return a feasible solution. So, and then for every instance of the optimization problem and some given algorithm that's consistent, so it returns always a feasible solution, but it does not necessarily have to compute an optimal solution. That's what we're looking for in the approximation regime. So we define the relative error of this algorithm on a specific instance as just the difference to the optimum, but divided by the optimum value, so that you normalize. It's the normalized difference to opt. And a number that's a bit more nicer, and it's just a bit nicer to handle, is the approximation ratio. And that's also what you find in the literature. So this is the number that we usually use to judge the quality of an approximation algorithm. You take just the, well, 1 plus the relative error in a sense, so that you always have a number greater than 1. So for example, the 2 approximation would mean that this epsilon is bounded by 1, which means that the difference between the actual solution you give and the optimum can be up to the size of the optimal value. So we're always at most twice as bad as the optimal. As the optimal solution. Okay, now the maybe simplest optimization algorithm brings us back to one of the simplest NP-hard problems, and that's vertex cover. So you certainly recall we have given a graph and we're supposed to select a set of the vertices so that all edges are covered, so that, which means one of the endpoint of the edges must be in the chosen set of vertices. We found that vertex cover is one of the easy problems in the sense that there's a good fixed parameter tractable algorithm for the problem. And we will see that it's also among the easier problems for approximations, even though not among the easiest. We'll come back to that at the end. So we will first discuss a few techniques and algorithms for finding approximation algorithms, and in the end we will quickly touch the theory how to prove that certain approximation ratios are not possible to attain. Okay, we need a simple definition. That's the definition of a matching in a graph. If we're given a graph, then a matching is a subset of the edges. Exactly if no two edges in M share a vertex. So let's just do a very simple example. A graph with a few edges. I don't know. And then you can pick a certain subset of the edges so that they don't touch. For example, like this. And the important point is that we don't touch any vertex twice. So matching, in a sense, is it's like a marriage, like it's sometimes called. You marry a few of the nodes, and it had better be disjoint marriages, otherwise there's trouble ahead. We additionally call such a matching saturated or inclusion maximal, which I guess prefer because it's very specific about what it's actually meaning. So that means it's a matching to which I cannot add another edge. And I think in the case of this graph that I've drawn here, I can't add another edge because there's no more two vertices left in the graph. So this is actually inclusion maximal. Well, this name, of course, comes from the fact that among all the subset of edges, the partial order of the subset relation forms a certain structure and has maximal elements, and these are exactly the saturated matchings. So let me add that a saturated matching is very easy to find. A trivial algorithm that's certainly not optimal is just start with an edge chosen arbitrarily and then for each edge in M, try to add E, and you do this until no more additions are possible, and then you get a saturated matching just by definition. There's certainly a way to do this a bit more efficient by using data structures, but conceptually a saturated matching is a very, very simple thing. Now let's add a third point to the definition. We call a matching, okay, let's make a room here. We call a matching just maximal. So this was no additions possible. Whereas maximal is just in the ordinary sense maximal cardinality. If there is no larger matching that contains more edges. Maximal matchings are a bit tougher to compute. So there's no very simple algorithm that would be on par in simplicity to this one, but there's sometimes the so-called blossoms algorithm. You can look it up. That's based on alternating paths, and these blossoms are kind of flowery structures in the graph. It's a bit of a childish name maybe, but there's an algorithm to compute maximal matchings in arbitrary graphs. So these are both kind of simple things. Matchings are kind of easy, whereas vertex cover, of course, you remember, is NP complete. And we make the following simple observation. Any inclusion maximal matching M is a certificate, proves that the minimal vertex cover needs at least half of the vertices in this matching. How's that? Well, for every edge in the matching, this has two endpoints. In the vertex cover, let's call this C. C has to contain U or V, or maybe both, but at least one, because it has to cover E. Well, since all the edges are disjoint in a matching, we need one node per edge in the matching, and that's sorry, that was bogus. We need exactly the number of nodes that we have edges in the matching. The point is that each edge actually has two nodes in the matching, so we will in a second see how these two connect. But whenever you find a matching, an inclusion maximal matching of a certain size, then you know that a vertex cover has to cover these edges and needs at least so many nodes. in fact, we haven't used where did we use that? The matching is inclusion maximal. So we've shown that any vertex cover has to take one of the nodes from each of the matching edges. And so I think this is just true for any matching, right? The point is that we just get more interesting lower bounds if we use these. At this point, we can leave it out. It's just any matching gives a lower bound on the vertex cover size. And we can actually make this an algorithm. So the algorithm would be compute a saturated matching or an inclusion maximal matching. And I just sketched that this is actually an easy algorithm. And then pick one vertex of every edge in the matching and return this. So this is a two approximation algorithm for the vertex cover problem. What we have to show first is that what we return is actually a vertex cover. And that's why we need inclusion maximal here. So here we just said that any matching gives a lower bound on the vertex cover size. But if you just add a very small matching where you can add more edges, what you get is not necessarily a vertex cover. So we have to show that this is a vertex cover. If we take any of the edges in the graph, we have to show that it's covered. So if this is the edge UV, then we either return U or V in our vertex cover. Well, towards a contradiction, assume not. So both U and V are not in C. By the definition of our algorithm, that means that also the edge E is not in our matching, in the inclusion maximal matching. But this means, this is not a good way to start. So the point is that since M is saturated, every edge E has one endpoint touched by M. So every edge, there must always be one of these edges one of the endpoints must be somewhere in the matching, otherwise we could add that edge to the matching. That's the way. Without violating the matching condition, and that means M would not have been a saturated matching. So by the observation from above, that means that this gives a lower bound on the optimal size of a vertex cover, because we have to cover all of these edges. Now what's the cost of our algorithm? Let's call it A. That's actually exactly M, because we return for every edge in the matching, we return one of the endpoints. Oh, sorry, I screwed up completely this part. This doesn't give you a vertex cover. So you pick both vertices of the edges in M. Okay, sorry, that was confusing. So the algorithm is you compute a maximal matching, but you pick all the vertices in M. Otherwise you would not cover all edges, and that's why it didn't match the nodes. The cost of this algorithm is 2M because it picks both endpoints for the match for every matching edge. And so the approximation ratio is just the cost divided by opt, which is 2M divided by opt. And as we know here, opt is bounded by the size of the matching. So the approximation ratio is 2. So this simple algorithm, now that I got it correct, just gives you an approximation for the vertex cover problem. Pick any matching and pick all touched vertices. Now you can improve this algorithm if you not only pick an inclusion maximal matching, but an actually globally maximal matching. But the point is you can't improve the analysis, so you still, in the worst case, only get this 2 approximation. I don't know of a way to show something better than that. And in fact, immediate questions that you should have regarding this algorithm. Can we improve our analysis for the approximation ratio? Maybe there's a clever way just to show that we achieve 1.5, not 2. But the answer is no, because we can give tight examples. We'll do so in a second. Let's just prove that this is tight and there is in general no way to improve the analysis. The second question is, can we improve the algorithm, e.g. by using maximal matching, as just mentioned, and not only inclusion maximal. But the reason here again, the answer is no, and the reason is the same examples actually show that the maximal matching there gives only this approximation ratio of 2. So you won't succeed along this line either. So that means if you want to improve that approximation ratio for vertex cover, you need a different idea for a lower bound. For the vertex cover size. And that's actually an open problem. It's up to now not proven either way. So no one has found an algorithm with a constant approximation ratio. There are algorithms that achieve something like 2 minus a function of n. But if you want to have a constant approximation that does not depend on the size, nothing better is known. And it's been proven that unless p is np, in which case vertex cover would be solvable in polynomial time. So, well, I mean, all of this is with respect to polytime algorithms. I didn't say that didn't even mention it, but of course I can always approximate the problem precisely ratio 1 if I just solve it exactly. The point is that this is probably not doable in polynomial time. So we're interested in polytime approximations all the time. And unless p is np, there's a lower bound on the approximation ratio. That actually proves that a certain ratio is not possible. You can't go below 1, 3, 6 or so. It's a wicked number. And there's a conjecture, the unique games conjecture, that implies 2approx is optimal. But it's also open whether this conjecture holds. It's a conjecture after all. So all we know about vertex cover is that there's a very simple and very efficient 2 approximation, but we don't know whether it's optimal, but it actually seems quite likely to be optimal. Oh, that was the wrong. Now I promised to give you a tight example for vertex cover that proves that you can't do better with this matching idea. So one example is the complete bipartite graph. So you have an even number of nodes, and you add just all the edges from all the nodes here. But none in between. So say we have n nodes here, n nodes there. Then an optimal matching is, for example, just all the horizontal edges. So you get n edges. So algorithm A above would give you 2n nodes in the vertex cover, which is just great. Take all nodes, that's a vertex cover. Thanks a lot. Whereas certainly an optimal vertex cover in a bipartite graph is always just to pick the complete left side. so this is this just shows that picking both endpoints can't get you better than an approximation ratio of 2. We can actually give a second such example. That gives you the same bound. You take the complete graph on an odd number of vertices. Then the maximal matching, also in the global sense, uses n-1/2 edges, because there's always if it's odd, then there's always one node that you can't match. But apart from that, since all edges are present, you will always find a way to match the subset of n-1 nodes. But you can show that the size of an optimal vertex cover is n-1. So what this shows is there's also cases where you actually have to take both endpoints from all of the matching. So let me add, the conclusion up here was in some graphs, one node per edge suffices. And in other graphs, no single matched node may be left out. So since we don't know in which kind of graph class we are, we can't in general improve our algorithm by too much, because we just, by looking at the matching, we don't know which case we have. And so usually we have to include all of the vertices. But there's also cases where this is actually every single one, every edge where we include both points actually takes us away from the optimum. So that means there's just no way to improve one or the other. So we can't improve the lower bound and we can't improve the algorithm in the general case. And I just want to add one further remark on that. As we discussed before, the vertex cover problem is NP hard, or NP complete. But the maximal matching problem is actually in P. So it's there's a certain mismatch, and you might ask where that comes from. First of all, vertex covers in NP because there's a yes certificate, namely the vertex cover. The maximal matching is in NP because there's a yes certificate, which is the matching itself. That's trivial. How about no certificates? If we can show that there's also a no certificate, the problems would also be in co-NP, and that would give us some insight maybe why one is easier than the other. And well, if we look at bipartite graphs, you can actually show that the size of the maximal matching always equals the size of the minimal vertex cover. Which is essentially a trivial observation, because this match, well, if the graph is not very complete, it's maybe not so trivial, but there's, from a bipartite graph always has these two sides, and then you can check what's the set of vertices that you can reach from this vertices, and it must be disjoint, so we will come back to that later when we talk about LP duality, and then we will find an easy way to prove this rigorously without now discussing hand-waving graph classes. But the point is that if you have that these two are actually equal, that gives you no certificates for both problems, because vertex cover then must be greater than the maximal matching, and you can actually give a certificate for the maximal matching, right? And since we know in this case that's actually equal, we can use the yes certificate for the matching problem as a no certificate for the vertex cover problem. If we just find a matching that's larger than the vertex cover size we're asking for, then we know, since they have to be the same, if we find a matching that's smaller than the vertex cover size, then we know we need so many, vertex cover is the minimization problem. So if we find a matching that's larger than the threshold we are given, we know we can't cover all these edges with fewer nodes. Right, so if we ask, is there a vertex cover with size at most k, then the no certificate is any matching of size greater k. So this is always true, but in bipartite graphs we also know there must be one such matching that we can actually find. And the same is true vice versa. For the maximal matching problem, we can use a vertex cover as a no certificate. That means on bipartite graphs, vertex cover and maximal matching are in NP and co-NP. And well, we actually know that they're in P both. Now I sketched that, I claimed that the maximal matching problem is actually in P because there's an algorithm for it in the general case. Why does that not contradict that vertex cover is NP complete? The point is that this match of the optimal values no longer holds if we don't have a bipartite graph. And the smallest example where you can see that is just such a triangle. The maximal matching just picks one edge, but the size of the minimal vertex cover is 2. So here, min vertex cover in general can be strictly larger than the maximal matching. And that means for some loose values of k, we can find a no certificate. But in general, we can't use the no certificates from matching to decide vertex cover, which we also didn't expect since it's an NP complete problem. Okay, that's for the introductory example of a simple approximation algorithm. Next time we'll look at a combination of randomization and approximations which actually play well together. And then we'll see a few more sophisticated examples of approximation algorithms.